Hey everyone, we're going to be going over the problem max area of island. So this problem is very similar to the problem number of islands. And if you're not familiar with what that problem is, you can go to one of my other videos where I explain how to solve it. But yeah, max area of island and number of islands, they're very similar, but there's subtle differences in the implementation. So the problem description says, given a non-empty 2D array grid of zeros and ones, an island is a group of ones representing land connected four-directionally, horizontal or vertical. You may assume all four edges of the grid are surrounded by water. And we have to find the maximum area of an island in the given 2D array. If there is no island, the maximum area is 0. So I'm going to switch over to the whiteboard and I will explain how to solve this problem. So in this first example, we have a grid that contains zeros and ones, where a 0 is represented as water and the number 1 is represented as land. And what constitutes an island is there needs to be at least one number 1 inside of one of these cells inside of our grid. And so we need to find the maximum island. So let's draw out what all of our islands are for this example. This would be one island. This would be one island. This would be one island. And then finally, this would be one island. And the reason why these are all islands and they're connected in this way is because all of the number ones that are tied together are connected horizontally or vertically. So for example, in this middle island, since this number 1 is connected to this number 1, and then this number 1, or maybe it'd be easier to represent it like this. These two are connected like that. These two are connected like that, that, and then finally like this, right? So all the number 1s are connected horizontally or vertically. And so we need to find the area of each of these islands. So if we were to count the number of ones inside of each of these groupings, we would get 3 for this island, 1 for this island, 6 for this island, and then finally 2 for this island. So if we were writing a function to find the maximum island for this input, we should expect 6 to be returned. So how do we solve this problem? What we need to do is we need to iterate from left to right over all of our grid. And every time we encounter a number 1, which means we have hit an island of at least the size 1, then we need to pretty much write a recursive function that will go from that number 1 and check all of its neighbors up, left, right, and down, and check if its neighbors is also a 1, and we continue doing that until we no longer find any number 1s that are connected horizontally or vertically. So I know that may sound a little confusing, but let's try to display this visually. So we want to iterate from left to right over our grid, and we only care about when we encounter a number 1 because that means we have found an island, right? So we're first going to iterate over the 0, we don't care. And then we get to this number 1, right? This means we have found an island. And so what that means, we can immediately have maybe some counter, right? So let's say area. That will be 1 because we have encountered a number 1. But now we need to find all number 1s that are connected horizontally or vertically from this number 1 that we have just encountered. So what we're going to do is we're going to check left, right, up, and down from this position. So to the left of this number 1, right, it's a 0. We don't care about that. We check right. Once again, it's a 0. We don't care. And we look up. There's nothing above us. We don't care. But then we look down, and we have encountered another number 1. So essentially, we just need to do the same logic that we just performed on this number 1 now. So we found another 1, so now we just increase our area to 2. And then we check above us, below us, to the left, and to the right. So we're going to look left, we find a 0, then we look right, we find another number 1. And so since we find another number 1, we're going to perform the same logic that we did for both of these other number 1s. But first, let's finish checking above and below us for this. So we're going to look above. Although this is still a 1, but we've already checked it. So we do not want to increase our area because we've already accounted for that number 1 in this island. And then we're going to look down, and we encounter a 0. We don't care. And so now we go to this next number 1 and do the same things. We find a 0 above us, 0 to the right of us, 0 below us, and then we find another number 1 to the left of us, but we've already accounted for it. So we only need to increase our area once up to 3. And since we didn't find any number 1s from this position any further, that means we have finished our pretty much we're done looking for this island. We know that the area for this specific island is 3. So this would be our max area. Our max would be 3 because we calculated our area to be 3, and this can just go back down to 0, right? But something to keep in mind is we want to make sure that we do not recount the same number 1 that we may have already accounted for, right? Because like right here, if I was checking above, I've already accounted for this number 1, so I don't want to recount my area. So one way that we can get around this is every time we encounter a number 1, we tally up the area and then immediately change it to water, because we don't care about water. So when we go and check above us again for this number 1, we're just going to find a 0, and we're not going to retally for that place. So that is how we're going to handle this part of the problem. So that will be changed to a 0. This will be changed to a 0. And then this would be changed to a 0. And we've already accounted for that area right here because we have a max variable keeping track of the maximum area we have found thus far as we're iterating. And so once we've done that, we just continue iterating through our grid. And we're going to continue on from here. So we're going to find a 0. We don't care. All of these zeros, we're going to iterate, and we don't care about it. And then we're going to find a number 1, right? We're going to look above us, to the right, to the left, and below us. We find all zeros. And so since we encountered this number 1, this area gets changed to 1. But we didn't find any number 1s horizontally or vertically from this position. So that means we are finished, and we need to compare what the area is compared to the max. So specifically, we need to get the maximum number between the area and max. So since 3 is greater than 1, we don't have to do anything. And then our area gets set back down to 0. And once again, since we encountered a number 1, we will immediately change this to a 0. And then we're going to continue iterating. We ignore all the zeros, and then we find another number 1. And so since we find this number 1, this we will check in all directions, and we actually find 2 number 1s horizontally or vertically to us. And so before we do that, we're going to change this number 1 to a 0. and then it doesn't matter which one you check first. So let's just check the right one first. And also, since we encountered that number 1, we're going to increase our area to 1. Okay, and then we're looking at this number 1 right here. There are no number 1s horizontally or vertically from this position. So we're going to immediately change this to a 0. And we're going to increase our area from 1 to 2. Then we're going to check this number 1. We look above us. This was changed to a 0. And we look to the left of us. We find a number 1. We look below us. We find another number 1. Oop. And then we look to the right of us. We find a 0, right? So we're going to increase our area once more and then set this number 1 to a 0. And then we can check another number 1. So right here, we find a 1 below us, and then all of the other directions are 0s. So this gets changed to 4. This number 1 gets changed to a 0. And then we're going to shift over to this number 1. We check above us, to the right, and to the left. And we encounter a 1, obviously. So we're going to change this one to a 0 and increase our area. And then finally, we check the very last number 1. Since there are no number 1s horizontally or vertically from this position, this gets changed to a 0 as well. And our area gets set to 6, right? And now we have no other number 1s to check for that island. So we compare area to max. And since our area is greater than our max, what that means is our area gets set back down to 0, but also our max gets overridden to be 6. And then once again, we're going to continue iterating through our grid. We find all 0s over here until finally we get to the very last 2 indices, and we find 2 number 1s. So as you can already imagine, both of these number 1s are going to be set to 0s, and our area is going to get set to 2. But since our max is already greater than the area, we don't have to do anything. So our area will just get set back to 0. And then finally, we're going to finish iterating over the last 2 indices. We find 0s, and that means we're finished. So by the end of iterating over our grid, we should have this max variable assigned to the number 6. So I'm going to jump into the code, and I'll show you guys how this actually looks like. So I'm going to be implementing the depth first search approach, and specifically I'm going to do it recursively. I find that the recursive solution is much easier to write in comparison to the iterative approach. Both the recursive and iterative approach have the same time and space complexity, and the recursive approach is much easier to understand. So that's the way I'm going to do it. So the first thing we're going to need is we're going to need a variable called max, like we talked about, and we can just initialize this to 0. And this is going to keep track of the maximum area that we come across. And then we're also going to need to extract the lengths from our grid. And this is just so to make our lives easier. So we can say n is going to be equal to grid.length. And then m is going to be equal to grid at the 0th index dot length. Okay? And then we're going to iterate over our grid. So we can say for an I less than n, j is less than m. And like I said before, we only care about when we encounter a 1, because that means that we have found the start of an island. So what we want to do is we want to say if the grid at position ij is equal to the number 1, then we want to count the number of ones that are connected to this number 1 that we have just come across. So what we can do is we're going to write another function that's going to return the area starting from this position that we have found. So we can say int area equals get area, and we're going to need to pass in a couple things to this helper function. We're going to need to pass in the grid because we need to know where the number 1s are in our grid starting from this position. We need to know what position we're currently at, so we need to pass the I and j values. And then just to make our lives easier, we're going to pass in these grid lengths. You don't have to assign these grid lengths to variables, but I just find it, a lot easier to read. So we're going to pass n and m, because n is the number of rows that we have, and m is the number of columns that we have, right? And so assuming that this get area helper function is already wrote, what we want to do is we want to say max is equal to math.max max in area. So this will always assign the greater of the two, right? And then by the end of iteration, we will have the maximum area. So we can just return max. So the only thing we need to do is we need to implement this helper function get area. So this helper function is going to be a recursive function, like I mentioned, and it's going to return an int, returning an area. So we can say private int get area, and we are passing in our grid. So let's assign that grid. We're passing in the positions and then the lengths of our rows and columns, right? And so since this is a recursive function, typically in a recursive function, you have a base case, and then you have the content that you want to write in your recursive function, and then you return. Usually you return the same recursive function, and then your base case handles the exit condition, right? So what are our exit conditions? Our exit conditions are if our current position is not inside the bounds of our grid. So what do I mean by that? If we go back to this example, let's just say that this position right here was a number 1, right? So if we were to check above of this number 1, we would be going out of bounds. We'd be checking an out of bounds number for this grid, right? So we need to check for out of bounds. That's one base case we need to check for. And then the second is when we encounter a 0. So if we looked left, right, or down from this number 1, we encounter zeros, but we don't care about zeros. So check for bounds. That's the first thing we need to do. And the second thing is check if the position is water, also known as just a 0. Those are our exit conditions. So let's write that. We can say if I is less than 0, if our row number is less than 0, or our column number is less than 0, or I is greater than or equal to n, because remember, n is the number of rows that we have. And since, obviously, this is 0 based, if our I value is equal to the number of rows, that means we have gone out of bounds. And then likewise, or j is greater than or equal to m, if our column number is greater than or equal to the number of columns that we have, that's out of bounds. And then so all of this is for the first base case or exit condition. And then the second exit condition, we need to check for a 0. So we can say or grid at ij is equal to 0. If this evaluates to true, then we could just return 0, because that means we did not find any area, right? And the reason why we can do this grid ij equal to 0 here is because if any of these statements are not true, if they are true, then that means that we will exit immediately and return 0, and we won't get to this part. But if all of these statements are false, that means we are at a valid position, and then we just need to check the position and see if it's a 0 or a 1. So if we get past this if statements, we know that we have a number 1, right? And remember, when we encounter a number 1, we did several things. We check left, up, right, and down for 1s, right? And then the second thing we did is we changed the 1 to a 0. And doing that was so that we don't count the same number 1 again when we're going through the recursion. So let's implement both of these things. So we can say grid ij is equal to 0. So we're assigning the current position, which is a 1, we're just setting it to 0. So that was this part right here. And then now we need to check left, up, right, and down. So let's do that. We can say in left, we're going to call get area, and we're going to pass in the grid. And we're going to say I, j minus 1, and an m. All of those inputs are the same. We're going to check to the right of us. And we're, instead of doing j minus 1, we're going to do j plus 1. We're going to check above us. And for this one, we need to say I minus 1, because this is the row. So n and m. And then finally, we're going to go down. And this will be I plus 1. Right? And so now that we have checked, we're checking recursively for the left, right, up, and down neighbors, the last thing we need to do is to just calculate the area, because we haven't done that yet. So what we need to do is we need to say return left plus right plus up plus down. And then the last thing we need to do is say plus 1. So this plus 1 may seem a little confusing. The reason why we do that is if you imagine if we didn't have this plus 1 here, get area would never be greater than 0, because we're only returning 0 in the base case, right? So we have to say plus 1, because that plus 1 is accounting for the current position. When we assigned that 1 to a 0 here, this 1 accounts for that. It's counting the current number 1 that we're looking at. And then we're calling recursively to all of the neighbors and appending whatever we find in those recursive nested recursive functions. We add it to this number 1 that we know there is a 1 at the current position that we found. And so that is how you write the recursive function. We can just submit this now to make sure that it properly works. And as you can see, it passes. So the next thing I'm going to do is I'm going to go over the runtime, time complexity, and space complexity. So the time complexity of our solution is going to be n times m, where n is the number of rows that we have in our grid, and m is the number of columns that we have in our grid. So if you imagine we're iterating over all of our grid right here, right, from line 11 to 18, we're only ever going to touch each element in our grid a single time. And that means that we're going to touch every single number in all of the rows and all of the columns, so it's just n times m. And then as for our space complexity is also going to be n times m. So if you can imagine, in the worst case, if we had our entire grid filled with ones, right? That would mean as soon as we encounter that first one, when we see the very first element in our grid, we're going to immediately start calling this recursive function over and over and over again for the entirety of all of the grid. We're going to touch every single element inside of our grid recursively. And so our recursion depth is going to be whatever the size of the number of elements that we have in our grid, which is n times m. So that is how you solve this problem. Thank you so much for watching, and I'll see you guys in the next one.